So the first thing we got to do is complete the table. And notice this phrase right here. This is AP's phrase they like to use right here. Complete the table of values for g of x over the consecutive equal length input value intervals. And we're going to see them use this, like you can see down here. Consecutive equal length input value intervals. What I am about to show you from what we're looking at here only works if we have consecutive equal length input value intervals. Okay? That means that we're looking at input values, so those are x's, right? We have to have equal lengths between our intervals, and they must be consecutive in a row, right? All that means here is that your x values have to be increasing at a constant rate. So like on this table right here, your x values increase by 2 as you go down the table. The consecutive equal length input value intervals do not necessarily have to be any specific number. Your x values could be increasing by 1. They could be increasing by 2, like we see here. They could be going up by 5s. They could be going up by 12. They could actually, the x values could actually be decreasing as long as they're like decreasing by the same amount each time, right? So this has to be true for any of the other things that we're about, other conclusions that we're about to make to be true as well. So we're doing the quadratic function g of x equals x squared. To make our table, all we have to do is plug those numbers into this very basic quadratic x squared, right? So we're just squaring the x value. So negative 3 squared here is going to give us 9. Negative 1 squared is going to give us 1. 1 squared is 1 also. 3 squared is 9. And 5 squared is 25. Okay, so if I am checking to see if this function is linear, then I need to look at the rate of change of that g of x column, right? So I'm going to look at what's happening to my y values. From 8 to 1, I have decreased 8, so it's minus 8. From 1 to 1, actually, nothing happens. That's just a 0, right? From 1 to 9, from 1 to 9, that's going to be up 8. And then from 9 to 25, if I do 25 minus 9 there, I'm going to get up 16. So, is this function linear? Definitely not. I mean, it was x squared, so it's clearly not linear. But, you know, even if we didn't know what the formula was, this function is not linear because if we have a linear function, we should be seeing the same number each time, a constant rate of change. So we definitely do not have a linear function here. But I want us to notice something about what's happening, right? My average rates of change here, I could do slope formula to find this, but I already have my change in y, and I already have my change in x. So if I want to do the average rate of change here to find the slope between the endpoints where x equals negative 1 and x equals negative 3 and x equals negative 1, all I've really got to do is do negative 8 over 2, which will be negative 4. And then I'll have 0 over 2, which is 0. I've got 8 over 2, which is 4. And I've got 16 over 2, which is 8. There. So if I'm looking at the average rate of change, definitely not a constant average rate of change, but what if I think about the rate of change of the rate of change, right? Like if I think about how the rate of change is changing here. From -4 to 0, that value goes up 4. From 0 to 4, up 4 again. From 4 to 8, up 4 again, right? So my average rate of change was not constant, but the rate of change of the rate of change, right? Like if I look at the rate of change again, is constant here. We could say that our average rates of change here are linear, right? Here where it says, what do you notice about the average rates of change of g of x over consecutive equal length input intervals? We could say something like over consecutive equal length input intervals the average rate of change is increasing at a constant rate. Now, the cool thing about this is you actually don't even have to look at the average rate of change. You can shortcut this a little bit because as long as you have consecutive equal length input value intervals, meaning that the x coordinates are increasing at a constant rate, then watch, like let's say I didn't actually find the rate of change, like do the -8 over 2. Let's just look at these numbers, -8, 0, 8, 16, right? If I look at what's happening here, that is an increase of 8. This is an increase of 8. This is an increase of 8. So this is always going to be true. If you have your average rates of change increasing at a constant rate, then this, what we call a second difference, is going to be constant. This could be called your first difference. And you actually can do this like again and again, and you'll have like a third difference and fourth difference and whatnot. There. So if your second difference is a constant number, like 8, 8, 8, 8, all the way down, then it guarantees that you have a quadratic function for that. So we are going to see a lot of questions that just ask us. They give us a table. They ask us, determine if the function could be linear, quadratic, or neither, right? So the first thing that you want to look at is consecutive equal length input value intervals, right? Do I have consecutive, oh gosh, what was it again? Consecutive equal length input value intervals. Do my x's go up by a constant number? Because that has to be true before you can do the first difference and the second difference, okay? If that's not true, you have to approach the problem a little bit differently, okay? So, if I look at these three tables, which ones have consecutive equal length input value intervals? A and C, right? So I can, on A and C, I see that x is increasing by 1 the whole time here. You don't actually have to even write that down if you don't want to. I don't know why it's losing its mind right here and shifting everything around. So I can just go over here and look at what's happening. From 0 to 1, that's up 1. From 1 to 4, that's up 3. From 4 to 9, that increases by 5. So does this table represent a linear function? No, because I did not get the same number here. But if I want to know if it's quadratic, I just do it one more time, right? So from 1 to 3, that is up 2. From 3 to 5, that is up 2, right? So I'm seeing that second difference is constant, right? So this table should be a quadratic. Okay, I'm going to skip B for now because our tricks are not going to work on B because we do not have consecutive equal length input value intervals, right? But on C, I do have consecutive equal length input value intervals because my x's are increasing by 2 each time. So I'm going to look at my y values, and I see that my y values increase by 2 here. The y values increase by 1 here. And then the y values increase by nothing here, right? Or decrease by nothing, whichever way you want to think about that. Does table C represent a linear function? No, because I'm not getting the same number right here. But if I do the second difference here, if I look here, from 2 to 1, that goes down 1. From 1 to 0, that goes down 1. So this table is also quadratic. Okay. These tricks do not work on B. Honestly, I don't think we're other than graphing and looking at it, using a different method, you're not going to be able to tell a function is quadratic from a table only like B, right? So this is probably either linear or neither here. So since we do not have consecutive equal length input value intervals here, we see that x increases by 1 here, and then x increases by 3 here, and x increases by 5 here. We are only going to really be able to check to see if this is linear. So I'm going to go over here and look at my change in my y values. So I see an increase of 1, an increase of 3, and an increase of 5. That looks like A, which was a quadratic, but x values are not increasing by the same amount, so we cannot make that assumption. What we can do here is we can actually find the slope, right? So if we find the slope, let's fix that. Let me erase slope. Why is it freezing up on me? Delete that. Right now, let me write slope. Slope is just our change in y over our change in x. So, for that first set of points, we do 1 over 1. That gives us 1. Here we do 3 over 3, also 1, right? And 5 over 5, which is also 1. So the slope between the points, no matter which points we pick, we still get 1, right? So this is linear, even though it does not immediately appear to be linear whenever we're looking at the problem. Okay, we can tell if a function is linear by analyzing the slope. We can tell if a function is quadratic by looking at that second difference, as long as we have consecutive equal length input value intervals. We can also tell a little bit about concavity, right? So here they tell us for a graph to be concave up, the average of change over equal length input value intervals is blank for all small length intervals. Okay. Notice they don't say average rate of change. I think they should take that of out just to be grammatically correct. But he did not accidentally forget rate of change here. It's not just a typo. So the average of change over equal length input value intervals is blank. So that's because we don't necessarily have to look at the rate of change. We can just look at that difference, like how much our y value is changing, which could be your rate of change, but might not be depending on what your x values are changing by. So whenever we think about something that is concave up, I'm just going to draw like, oh wait, let me get a pen. Switch to the highlighter. Switch to the pen. Come on. Like this graph right here is concave up, right? If we think of taking like the slope of the graph, like on little intervals, like from here to here, I have this slope, and then from like I want like the same distance, like our x is increasing by the same amount, and I'm doing this little slope, and then I do this little slope, and let's do one more. This little slope right here. What is happening to that slope as we go from left to right? It's increasing, right? The slope of those little lines are increasing. The average rate of change on those equal intervals is increasing. So if the change on these intervals is increasing, for small length intervals, we can see that the graph is concave up. And in a similar manner, if we see that rate of change, or not rate of change, but the change is decreasing over those equal length intervals, then we're going to have a graph that's concave down. So we're going to do some practice with this here in a minute. It's going to have some questions to ask you if a graph is linear, quadratic, or neither. Then it's going to have some questions to ask you about concavity. And they don't want you to graph it. They want you to be able to tell from what we're looking at. So the first key always on this, you cannot know about concavity unless you have those, I'm going to highlight it again, same phrase. Equal length input value intervals. Equal length input value intervals, right? Your x values have to be increasing by the same amount each time. So like if I look at all three of these tables, all of my x values are the same for all three tables, and all of my x values are increasing by 0.1 each time you go down. So we have equal length input value intervals. If you do not, you can't answer the question, so they're not going to give it to you. There. So we're just going to look at the difference here. So 4 to 1, that goes down 3. 1 to -1, that goes down 2. And -1 to -2, that goes down 1. And so are these numbers increasing or decreasing? They're increasing. But I think I heard a couple of you say decreasing under your breath. And I would shame you for that. But I also did the exact same thing during first period. Because I said, look, these numbers are decreasing. And then I stopped myself. I was like, no, they are not. Because these are negative numbers, right? So -3 is down here. -2 is up here. -1 is higher. So these numbers are increasing. So since these numbers are increasing, this graph is going to be concave up. Another thing that you can do is you can look at the second difference here. So from -3 to -2, that is up 1. And from -2 to -1, that is up 1. So this one didn't ask us if the graph is quadratic, but is the graph quadratic? Yes. And because that number we're getting for the second difference is positive, that tells us that we're dealing with a concave up parabola. Right? For B, my table goes up 3, and up 3 again. Is this graph concave up, concave down, or neither? Neither, because what's this graph look like? Just a straight line, right? This graph is linear, and a straight line does not have concavity. It's not curved. So this one is neither, and I'm going to put because m of x is linear. And for our last one, from 1 to 7, we go up 6. From 7 to 11, we go up 4. And from 11 to 13, we go up 2. Okay? Are these numbers that we're getting here increasing or decreasing? Decreasing. So this graph is going to be concave down. Again, another way you can look at it, they didn't ask if the graph was quadratic, but we could look at the second difference. So this is down 2 and down 2. The second difference is negative and constant. So this tells us the graph is quadratic in this particular case, and that quadratic is concave down, since we're getting a negative number for our second difference. Okay, questions? Okay, so I just have a quick worksheet. Oh gosh. Yes, let's continue. Okay. On 4, I've got up 1, up 7, up, what do you get there? 19. What's the last one? 37. Okay, so if I do my second difference, that's up 6. This is up 12. This is up 18, I believe. There. So the first difference is not constant. The second difference is not constant. But what if we did it one more time? You are correct. So if the third difference is constant, then you would have a cubic. So the question didn't ask us to do that, but that would be cubic there. And you could do the same for like fourth difference and fifth difference and sixth difference. It would tell you that something's to the fourth power, or fifth power, or sixth power. They're unlikely to ask you that because they would have to give you lots of tables and it would take too long to like figure it out, right? But that's just a bonus there for you. For 7, that graph is going to be concave down. Again, he did the full slope. I wouldn't. I would shortcut that and just look at the differences because you have equal length input intervals, right? For 8, that's neither because the function is linear, right? So you don't have concavity whenever the function is linear. And for 9, that one is neither. It almost looks like it should be concave up. Again, he did the full slope right here. I would not. I'd say that's up 2, up 4, up 8. But then from 11 to 17, that's only up 6. So 2, 4, 8, those numbers are increasing, but then when you go down to 6, that number is decreasing. Or if you're looking at your second difference there, up 2, up 4, down 2. All of those second differences are not positive. Some are positive, some are negative. So you have some mixed concavity there. Okay, questions on those? All right, so we are going to move on looking at that initial polynomial that they've given us here, it looks like this section shall be torture. But I promise it is really not very bad at all. In fact, I would say that this section may possibly be the easiest section of the 4 that we have done so far. This is like some textbook sort of language right here, right? They are really making this mathematical here so that you, so that this particular polynomial would apply for any type of polynomial that you could imagine. However, you would probably have an easier time with it if I instead just had given you something like this, f of x equals 4x to the 5th power plus 2x to the 4th power minus 3x to the 3rd power plus x plus 2. Actually, let's put a number there. 1x to the 2nd power plus 4x minus 7, something like that. So if I gave you this, you would probably feel more comfortable in answering the questions that we have given you. But I'm going to sort of highlight the parts that correspond, right? So all of these like A's with N's behind them, with the little subscript of an N, those are coefficients. So like I've got A sub n minus 1, A sub n minus 2, A sub 2, A sub 1, A sub 0. Those are like the coefficients I've got here for positive 2, negative 3, positive 1, positive 4, negative 7. Okay? This just means like this is like if our function was to the 5th degree like we have here, right? This is the like 5th coefficient. This is the 4th coefficient. This is the 3rd coefficient. That keeps decreasing until you got the 2nd, the 1st, and the 0 or the initial condition coefficient that you have right there. So all of this in yellow, those are just coefficients. The x's are the variables, so I'm not going to highlight them. And then the n minus 1, n minus 2, that square, I'm going to highlight right here, and I'm going to highlight right here, but there's nothing there, right? But there could be a 1 right here, right? And I don't have an x here, but if I put 1, I'd have to have an exponent of 0 right there, right? So this n minus 1, n minus 2, and so on, is just showing that our exponents start with the biggest numbers, and then they're decreasing, right? That's the standard way for us to write a polynomial. Oh, gracious. My highlighter, not that. So our exponents, if we put the exponents in standard form, we would see decreasing exponents, right? Now, your functions are not always given in standard form. So if they're not given in standard form, then you have to find like the leading term that you're looking for, and it may not be the first term. So we can learn a lot of information from the leading term of the polynomial. Okay, the leading term of the polynomial is the term that has the highest exponent. Okay, so in this big long crazy expression, it's this one. So the leading term would be a sub n x to the nth power. But if we want to think about like a more simple example, in this equation, that leading term is 4x to the 5th power there. Okay, so the leading term is the whole term, like that whole piece, right? The number, the variable, the exponent, everything. The degree is just the exponent. It is just the highest exponent of the polynomial. So in the complicated expression, what is the highest exponent that we have? It's the n. Okay. In the one that actually has numbers plugged in, it would be 5. And then the leading coefficient and leading terms sound like they have to be the very first. And if your polynomial is in standard form, they will be the very first term. But sometimes, like in the examples to come, you don't have these functions in the standard form. So wherever your highest exponent is, the coefficient is the number in front of that. So the leading coefficient in this case would be a sub n. Or if we look at the polynomial that I wrote in up here, the leading coefficient is just 4. So write down your answers for the next 3 right here. Find the leading coefficient and the degree for each one of those functions. As I walk around, I'm seeing a lot of right answers, but I'm also seeing quite a few pieces that are wrong. Check with your neighbor and see if you guys are getting the same thing. Mostly on B and C. I think most everybody had A right. Okay, so I think a few of you fixed your problems on your own. Here are the numbers that you should have. I think almost everybody had 3 and 4 on A. That one looked good. On B, some of you had 12 as your leading coefficient. The leading coefficient, it sounds like it is the first term. But if the polynomial is not in standard form, then that's not going to be the case. So this polynomial that's given is not in standard form. The highest exponent is not written first. So the the -7 is your leading coefficient. There were also several of you that did have the 7, but you left the negative off. So you must include the sign in front of that term. So be careful with that. So you should have -7 and 3. And then the last thing that I saw was that a lot of you had a degree of 1 for the last problem. Okay? So what I like to do here to explain this is, like, if I put an x here, what does the exponent of that x have to be? If that exponent is 1, now this function is 4x. Is that what the function is supposed to be? It is not. It's supposed to just be 4. There's not supposed to be an x there. So what exponent could I use on that x that would, like, basically make it disappear? I could put a 0. What is anything to the 0 power? Anything to the 0 power is not 0, but 1. It's kind of odd. It's weird. We'll talk about why maybe later.
No, I am curious. What do you think 0 to the power of 0 is?
0 to the power of 0, I believe, is in a category of numbers that we call the indeterminate form.
Yeah.
Like another example would be 0 divided by 0. Like, you can't determine anything from that. We actually talk about it. We do 0 over 0 a lot in calculus. I believe 0 to the 0 power also shows up in that category. And it's indeterminate, so it doesn't really have like a number value that you can give to it.
Yeah, I'm just curious what your thoughts.
Yeah.
Other people disagree.
I don't know. I've not heard the
You
disagree.
You decide whether or not it's 1 or 0 or whatever.
Right. I'm going to have to look into that. I can tell, Michael, that you're going to be my James this year. Did you guys know James? Oh gosh, what's James' last name? No. Is it C? No. Ripley. Yes. Because he just moved from like Asheville here. Is that the one? Yes. You're going to be my James this year. Because you think about things very deeply and know sometimes more than I do on stuff. So I love to think about things like that. So give us all of your input for sure. James would do. James particularly when we did things in Desmos, I'd be like, you cannot do this in Desmos, and be like, James would be like, actually, you can do this, this, and this, and he was usually right.
I've broken Desmos before.
Yeah. Yeah. So, let's talk about why this is important, okay? Let's talk about why this is important. If I know the degree of the function, and we'll get into this in greater detail later, but it's going to help us on some on some problems that we have later. If I know the degree of the function, it can help me talk about the end behavior of the graph, right? Whether or not the ends of the graph go up or down, or one end goes up and one goes down, or like this, right? So if I have an even degree, in fact, let's skip there. This is in the notes, so let's get down here. Actually, no, maybe it's not. No, okay, no, I'm thinking of something else. It's not in the notes, but if I have even degree, then both ends of my function either have to go up, so I'm going to put like a box around that, or both ends of my function will go down. Okay, so like for A, I know that's the case. There is an exception for 0, because in the case of 0, you have a horizontal line, in which case the ends of your function do not go up or down, they just go out. So 0 is your exception to this. But if other than 0, if you have an even degree, you're going to see the end behavior happen as such. And I can also look at my leading coefficient to tell me whether it's up or down, right? So if I have a positive leading coefficient, then both ends of the graph go up. And if I have a negative leading coefficient, then both ends of the graph go down. If I have odd degree, then my end behavior is going to be opposite from each other, and we're going to talk about that in more detail later, so I'm just going to kind of leave it at this. This piece of information is what we need for this section right here. So let's keep moving. You may or may not have heard Miss Martin use the word extrema. Have you heard that before? So extrema is just a general term that keeps us from having to say maximums or minimums. If you're talking about the extrema of a graph, then you're talking about the maximums and the minimums of the function. And there are two types of extrema. I am certain that Miss Martin talked about the maximums and minimums of a function. That should be, something that you've seen before. Extrema is just a general term that means either one. You also should have learned about relative extrema, so relative maximums and relative minimums, and absolute maximums and absolute minimums, right? For this course, you may also see the term local and global. Local just means relative, and global just means absolute. It's just a different term that means the same thing. When I asked first period, they said they had not really seen local or global. Does look familiar. I mean, I know you've heard those terms, but in math, have you heard those? So these are just the same. To me, they make a lot of sense. For example, if you are, the best basketball player on Elkin High School's basketball team, you are the local maximum, right? You are better than all of the other players around you. So they may be in this room. I don't know. Could be. So the best basketball player in all of Elkin is the local maximum or local star, right? That is, they are relatively better than the players around them. The local maximum is not necessarily the global maximum. In fact, probably not the global maximum. The best basketball player on Elkin High School's team is probably not also the best player in the whole entire world, right? Let's hope not. At least not yet. Maybe one day. It could be. Maybe you're just not there. Just give them a few years, and it's going to be them. It's going to be Michael Jordan, LeBron, and Lauren. Or Bryson. I don't know. Could be. Do I have any other basketball players? What about the girls' team? Anybody on the girls' team? Could be Alyssa. Caitlin Clark, Alyssa. Could be one of the two. I don't know. So local just means relative. Global means absolute. And I am not certain. I can't remember for sure because the pre-calculus test is a lot earlier. It has only been around 2 years, and I have not looked at as many questions from it. But I know in calculus, the AP definitely uses those two terms interchangeably. And on the same test, sometimes you'll see, sometimes they're referred to as local, sometimes they're referred to as relative. So you need to know both terms here. Relative extrema, we typically only talk about relative extrema by their x coordinates. They're not usually going to ask you for the y coordinates of relative extrema. And I find this pretty crazy, but our definition of the relative extrema here, a polynomial has a relative minimum or a relative maximum where Mr. Passwater used the word it right here. That is pretty rude of him. I did not write this, but I also obviously didn't screen it for profanity well enough either. Wasn't expecting that of him, but maximum where the function or the polynomial switches between decreasing and increasing, or at an endpoint if the polynomial has a restricted domain. That last part is what is interesting to me because in AP Calculus, the definition that they kind of use as the standard there does not allow a relative maximum or minimum to be at an endpoint. They basically use the definition that the function switches from increasing to decreasing or decreasing to increasing and do not consider the endpoint. There are definitions where this can be true. What makes me wonder is why they would use a different definition for AP Pre-Calculus and AP Calculus. While both have like proper reasoning behind them, I don't know why they wouldn't be consistent between the two courses. Good news is they almost never are going to ask you the questions about the endpoints, so it's not going to end up being an issue really much at all there. So if we're looking at local or relative maximum and minimums, you must also know that absolute maximums or minimums are also local maximums or minimums, right? So if you have the global maximum, the best basketball player in all of the world, that maximum is also a local maximum, right? If LeBron James comes to Elkin High School and plays a game at Elkin High School, he is undoubtedly going to be still better than the people around him, right? So, probably. I don't know. We've had a decent season. Pretty good. All right, get a little shaky after Christmas. Yeah, we'll get it back together. All absolute maximums can also be considered relative maximums. So whenever we answer this question here, our local minimums are going to happen right here at x equals -4, at x, about messed it up. This point right here, x equals what there? 0, not -1. I just about wrote down -1 because that dot's right there beside of -1 just screaming for me to write it down. But it's not -1 because you have to look at the x coordinates, right? And then that would be it for your minimums. And then your local maximums are at -2, x equals -2, and x equals 3. Now, the same graph is on the next space over. So this graph over here is the exact same. But now they're asking us for absolute maximums or minimums. So in this case, the absolute maximum, whenever they ask you about absolute maximums or minimums, they may ask for only the x value or they may ask for the y value. If they are asking for the x value, they will say, find the x coordinate where the graph of f has an absolute maximum. So they'll specifically name the x coordinate. They'll say, find the x coordinate where this happens. If they're asking for the y coordinate, they're just going to say, find the absolute maximum of f of x. Most of the time anyway, right? They are not specifically going to tell you it's the y coordinate. The maximum is the y coordinate. The safest way to answer a question that's asking you about a maximum or minimum point is to say, here is the maximum which occurs at this x value. Okay, so if we look at this graph, the absolute maximum, the absolute highest point, is right here on the graph. I listed it as a relative maximum over here, but it's also the absolute maximum, highest point on the graph. So what I will do for an absolute maximum, the absolute maximum is the y coordinate. So the absolute maximum is 2, which occurs at x equals 3. Now, if they just said, what is the absolute maximum of f of x? You could just say 2. That would be the correct answer. But I like to answer the question like this. The absolute maximum is 2, which occurs at 3, x equals 3, in case I misread the problem, in case they wanted that x coordinate and I wasn't giving it to them. So that sort of like covers your bases. they won't get mad at you for getting extra information like the absolute maximum, the y coordinates too, if they were only wanting the x. But if you leave something off, you'll be in trouble. So, what's the absolute minimum for this graph? -3? You would almost be right, Judy, and I'm almost glad that you made this particular mistake, because this graph is meant to trick you. I'm pretty sure that he put this here to trick us, because there's that point right there. That's the lowest point. We got it. But what's over here on the end of this graph right here? Sneaky little arrow hidden up next to the 5. Almost looks like it's part of the 5. So that tells us that this graph keeps on going down, right? So is -3 the absolute minimum? It is not. But if that arrow was a closed circle or open circle, either one, then you would be absolutely right. -3 would be your minimum. And somebody fell for it in first period also. Like I said, I'm almost glad you did, because if I just gave that question on a test, there'd be several of you to miss it. It's tricky. You got to watch out for it. So there's actually none there. Okay. So a lot of these questions that you're going to see are going to ask for a lot of things, but they may not have a lot of those things. So for A, this asks for relative maximum, relative minimum, absolute maximum, absolute minimum. Right away, I see that I have arrows on both sides of this graph that are going down. So do I have an absolute minimum? I do not. Do I have any dips where I go back up where I would have a relative minimum? I do not. So they tell us to put NA for that, so I don't have any type of minimums for this graph. Okay. As far as a relative maximum, I really only have this one single maximum here, and it is my absolute maximum. But all absolute maximums are also relative maximums. So I would say I have a relative maximum at x equals 1. But if I want to talk about the absolute maximum of this graph, I need to give the y coordinate. The absolute maximum is 3, which occurs at x equals 1. Okay, try those next two on your own. There will be more than one on some of these. So if you have 2 relative minimums, just put a comma between x equals 3 and 7, whatever you got. As always, we are about to run out of time, so I'm going to go ahead and give you the answers here. There we go. All right, relative minimum is at x equals -2. Relative maximums are at -4 and 3. There is no absolute minimum on B because you have an arrow over here. And then the absolute maximum is 2, which occurs at x equals 3. For C, you have relative minimums at x equals -3 and +3. You have relative maximums at -4, 0, and 5. Somebody out there probably has -4, 3, and 5. But give the x coordinates, that 0 right there is the x coordinate. Absolute minimum is -3, which occurs at -3. And the absolute maximum is 4, which occurs at x equals 5. Hold on just a second. I'll pack it up. We got one more little thing I'm going to cover before we pack this up. Okay, everybody okay here? Makes sense? Okay, we're going to fill this in really quickly. Between two real zeros of a polynomial, there must be at least one relative maximum or relative minimum. And polynomials of even degree must either have a absolute maximum or an absolute minimum. Think about what we were talking about earlier, the end behavior of those graphs. If both ends go up, then there's no relative maximum, but there has to be a relative minimum, right? So you're going to see some problems at the end of your assignment that ask you to tell maximums or minimums, and you won't have that. The other thing they're going to ask you for is a point of inflection. A point of inflection is a point where concavity changes. So, like, if we just look at this graph, I'm going to run, if we look at concavity, this graph is concave up here. Then, in the middle, it switches to concave down, and then here, it switches to, oh, didn't switch colors, switches to concave up again. So, that means that here at, why is it not letting me write? It knows I'm in a hurry. That means your points of inflection are at x equals -1 and x equals +1. Sometimes they're a little hard to tell from the graph. Just go with like the closest whole number where you think that happens. Okay.